But in case of groups, if S is a group, if S is a group, then show that all these relations, they are actually equal. So in case of groups, they are not different. H is equal to D is equal to L is equal to R is equal to J. They are all equal, and they are all equal to the universal relation. So in case of groups, these relations are not actually important, but in case of semigroups, they are important. So in case of semigroups, there are the strict inclusions actually. So now we try to find a certain class of semigroups where the equality holds, say where D equal to J or where H is equal to D, like that. We try to find those classes of semigroups. In case of groups, they are always equal. So let's also, in case of commutative semigroups, if S is a commutative semigroup, if S is a commutative semigroup, then they are also equal. H is equal to D is equal to L is equal to R is equal to J, and it's not equal to S cross S. So they are equal but not all equal to S cross S. Maybe some proper sub-relation of this universal relation. And but they are equal. H is equal to D is equal to L is equal to R is equal to G if S is a commutative semigroup. So now that means these relations are actually important in non-commutative semigroups. So there is one more semigroup where these D and J, they are equal. In general, this D subscript J, but we will show that they are equal in certain class of semigroups. So let's first define that semigroup. Definition. As we have seen that the definition of finite monogenic semigroup, which is generated by A, it's actually this: A square, A power m plus r minus 1. It's a finite monogenic semigroup where this m, it's called the period of A, and r is called the index of A. And that order of A, it's actually equal to m plus r minus 1. It's the number of elements in the finite monogenic semigroup. As in case of groups, the order of a generator is equal to the order of a group, cyclic group generated by that element. And this is equal to period, it's period of A plus index of A minus 1. So that's it. That's order of A. And also we have seen that this finite monogenic semigroup, it contains a subgroup which we have denoted by K, and that K is equal to A power m plus 1, A power m plus r minus 1. It's a subgroup of finite monogenic semigroup. And this subgroup must have identity. That identity is of this form because it contains every element is the A power some natural number. So that identity is of this form: A power some n, where n lies in this, where n is greater or equal to m and less or equal to m plus r minus 1. This is an identity of K. But this is not the identity of the finite monogenic cyclic group generated by A, because it acts as identity only for those elements. It's an identity of the group K, which is a subgroup of this. But one thing that's important, which is this: A power n into A power n, both, since A power n is identity in K, A power n, they are both in K, it's equal to A power n. So that means A power n is actually idempotent. A power n whole square is equal to A power n. It's an idempotent of a finite monogenic, because it's an element of this also. So whenever we have a finite monogenic semigroup, then it must have an idempotent. It must have at least one idempotent, because that idempotent is actually the identity of the subgroup, which it has actually here. It's a subgroup of this, so it has an identity, and that identity is idempotent of the finite monogenic semigroup. So in other words, we can say every finite monogenic semigroup has an idempotent. Now we define periodic semigroup. A semigroup S is said to be periodic if order of every element of S is finite, or we can say the semigroup generated by every element of S is a finite monogenic semigroup, or order of every element is finite. So it means that therefore for all A belongs to S, there exists a natural number n such that A power n is an idempotent of S. Because A belongs to S, so it has a finite order. Therefore the monogenic semigroup generated by A is a finite monogenic semigroup, and that finite monogenic semigroup must has a subgroup, and the identity of that subgroup is the identity of the finite monogenic semigroup. Is the idempotent of the finite monogenic semigroup. Therefore, it is also the idempotent of the semigroup S, because that element must be also the element of S as well. So that element which is idempotent of the subgroup of finite monogenic semigroup is an idempotent of S. So that's A power some natural number. So that's why there exists n, a natural number, such that A power n is an idempotent of S. Okay, so now we'll see that this when the semigroup S is a periodic semigroup, then D and J, they are equal. D and J are equal relations. So that's our next theorem. If S is a periodic semigroup, if S is a periodic semigroup, then D is equal to G. Then D is equal to G. So D subscript J, that we'll see, is by definition actually. You see. Now we show that J is subset of D. Okay. J is subset of D. So let's take any pair in J. J is a relation. Let's take any pair in J. Let A is J related to B, or A comma B belongs to J. Then there exists X, Y, Q, B in S1. As we have seen, then there exists X, Y, comma U, B in S1 such that X, A, Y is equal to B, and U, B, A is equal to U, B, V is equal to A. Okay, this is the definition. So in order to prove that it belongs to D, what's D actually? D is equal to L composition. So we need to show that there exists C in S such that A, C belongs to L and C, B belongs to R. So we need to find that element actually. So to prove A comma B belongs to L composition R, we show that there is C in S such that AC belongs to L, or A is related to C, and CB belongs to R, or we can say C is R related to B. So we need to find this element actually to prove it's an L composed in R. Okay, let's use this equation. Actually, we have this equation: XAY is equal to B and UBV is equal to A. Let's use this equation. So we have A. What's A? A is equal to UBV. UBV. And what's B? B is equal to XAY. B is equal to XAY. B is equal to XAY. So A is equal to UXAYB. Let's again apply this relation. UX A is equal to UXAYB into YB. Okay. So it's equal to UX square into A into YB square. And you can continue this process. It's equal to UX power n A into YB power n for every n greater or equal to 1. And similarly, you can see this B. B is equal to XAY. That's equal to XA. A is equal to UBV into Y. So B is equal to XUB VY. This B is equal to, again, now you can apply this equation. B is equal to XU B VY into VY. So that's equal to XU square into B into BV square. And you can continue this process. You can see this is equal to XU square B YB power, sorry, it's power n now, power n for all n greater or equal to 1. So we have seen that A is equal to UX power n into A into YB power n for every n greater or equal to 1, and also this B, it's equal to XU power n B into B into it's here actually VY, I think it's VY, okay. XU power n into B into VY power n for every n greater or equal to 1. So these two equations, they are very important. These two equations are very important. So I will write these two equations here. What's A? A is equal to UX power n into B into V Y power n. It's A here, so it's A. And B is equal to XU power n into B into VY power, say I will write here M, for every n comma m greater or equal to 1. So we have these two equations. Now let's use these two equations. Since S is periodic, since S is periodic, so that means for every element, for each A in S, there is some natural number n such that A power n is an idempotent. Now, so there exists some m greater or equal to 1 such that UX power m is an idempotent. UX power m is idempotent, is idempotent of S. We can do this. So there is some power of UX which is idempotent. Now let's choose. Let's put this. Put X C equal to XA, or you can say XA equal to C, and we will see that some element times C is equal to A, so that will give A comma C. There the A is related to C. So by putting this, now I want to find an element, some other element, say I want to find some, say S, so that S times C is equal to A. Let's try to find that element here. So then I want to find this A. This should be equal to some element of S times C. So what's this A? A is equal to, as we have seen, that it's equal to ux power m, for every n, in particular for m as well, into A into Vy power m. So this is an idempotent. It's ux power m into ux power m into A into Vy power m. So it's equal to, now it's equal to ux power m, and this one it's equal to A. It's A, but I want yes, that's what actually I want. This A should be equal to element of S times C, not A. It should be here C. But how can I achieve that C? C is actually equal to XA. So I want this XA should be here. But this can be done because we can write it as ux power m minus 1 into ux into A. Okay. Now let's this one XA, it's equal to C, so it's equal to ux power m minus 1 into U into C. So now look at this. X into A is equal to C, and this A is equal to some element of S times C. So that's, you have this actually. So let's denote this element by D. So we have this D, C is equal to A. So thus there exist two elements, A and there's two elements X and D, such that XA is equal to C and DC is equal to A. So which implies A and C, they belong to L. They are L related by definition of the relation L, because there exists X and D such that XA is equal to C and DC is equal to A. So A and C, they are L related to each other. Now I will show that C and B, they are all related. C and B, they are all related. So now we show that C and B, they are all related. They are all related. They are all related to each other. They are all related. Okay. We have this equation C y is equal to Cy. What is the C? C is actually XA by our definition, XAY, but XAY is equal to B. So C times Y is equal to B. Now I will show that B times some element of S is equal to C. B times some element of S is equal to C. Now let us choose n greater or equal to 1, such that this Vy power n is idempotent. This because element of any element of S, for any element of S, there exists a natural number n such that element power n is idempotent. So Vy is an element of S, so we can find some natural number n such that Vy power n is idempotent. Is idempotent. Now we can see that. Now let's check this. C. Actually, I had to show that C is equal to element B times element of some S. So let's find this C. C is equal to, our C is XA, and this A is equal to its X times A. What's A? A is equal to it's equal to ux power any natural number n. Let's choose that natural number n plus 1 into a into yv into yv power n plus 1. Okay, this is already done, and that's equal to, so let's expand this. It's ux, and then I can write it as xu into xu power n plus 1, but there will be one x left here, which is x, and I can write it as xayv into yv power n. It's yv into yv power n. Okay, so that's again that's simple again, but we can write it as vy power n also, vy power n into v vy power n into v. So let's look at this. It's equal to xay, that's equal to b. It's equal to xu power n plus 1 into b, and this is vy power n into v. So first I expand yv, then I can write it as vy into up to n times, and there is one more v that's here. Okay, so it's equal to now, but vy power n is idempotent, so I can write vy power n as vy power n into vy power n, or you can see vy power n can be written as so this cy is equal to b. So let's cy is equal to b. So now vy power n is idempotent, so which implies this c is equal to xu power n plus 1 into b into vy power n into vy power n, because it is an idempotent, into v. Okay, so this one it's now equal to power n. It's equal to xu power n plus 1 into b into vy power n plus 1 into vy power n minus 1 into v. Okay, that's equal to, now this one, it's actually b. By construction, it's b times vy power n minus 1 into v. And let's write it as say it's equal to b times some element t, where t belongs to s. So that is bt is equal to c, where t belongs to s1. So it's done now. So thus there is y